Space and date. Right, here we are. So there's the ocean. Any questions? All right, it's a big area with lots of water in it, and there's quite a lot of it around. That might be volume. I'm not sure if I can raise the lights any more than this. I don't think we have a dimmer. So, yeah, sorry, I'm not meaning to leave anybody in the dark. But there's a little snapshot of what we call the hydrosphere. The hydrosphere being the total of all water present on the surface of the Earth. You can see, of course, the ocean. You can see clouds. In the far distance, I think I can see some rain falling down out of the clouds. As my son learned in, I think, first grade, you should know that solar energy makes water evaporate from the surface, go into the atmosphere in the form of vapor, and eventually come back down in the form of clouds. We call that the hydrologic cycle. Okay, it was working a minute ago. Where's the clicker? This. Yeah. Okay. You certainly don't have to memorize these numbers, but the global hydrosphere is 326 million cubic miles of water. The vast majority of it is what's in the oceans, a little over 97%. The vast majority of what's left is locked up in glaciers and ice sheets, although for how much longer, who knows? So the total amount of water that humanity has available for its use at any given time is less than 1% of the total that's there. Most humans, for drinking and things like that, we need fresh water. And available fresh water is less than 1% of your total water budget. Most of the available fresh water is groundwater. What is in rivers is 0.0001%, which is not a great deal, and that is what we primarily depend on. I did the math once, and I forget how it goes, but if you imagine that the global hydrosphere is a 5-gallon bucket, the amount of water that is fresh and available for human use works out to be something like 3 shot glasses. So the amount of fresh water that we have is a very small fraction of everything that's there. Even then, it may not be as much as you might think. Okay, here we go. If the global hydrosphere is a 5-gallon bucket of water, the amount that's not in the oceans is a little less than a large bottle of soda. Non-frozen sources of fresh water is about 3 shot glasses, and all of these surface fresh waters would take up a little more than a teaspoon. So the fresh waters that we've got are quite literally a drop in the bucket. Making the same point, if you could somehow gather the entire hydrosphere into a single drop, it would look like that sphere kind of centered on, looks like Nebraska. That thing looks like a blue marble. This is what the world would look like if you could suck off all the hydrosphere, leaving the Earth completely dry, and put the whole hydrosphere in the form of a single drop. That ball would be about 4/10 the diameter of the moon, or a little bit smaller than the largest asteroid. Well, except they now call it a minor planet. So it seems like a lot, but it's not that much. And if we zoom in a little bit, that 169-mile drop centered over Kentucky to the right of the Big Marble is the total amount of fresh water. And the tiny blue spot that's sitting on top of Atlanta, Georgia, that's the total amount of fresh water in rivers and lakes. And that's most of the supply that life on land depends on. Fortunately, because of the hydrologic cycle, that supply is constantly being renewed as water evaporates from the oceans or from everywhere on the surface, passes into the atmosphere, and then comes back down as rain. So that 35-mile drop is constantly getting recharged. Some of the water that falls on land percolates down into the ground and recharges groundwater. So those, some of it falls in the form of snow and packs down into glaciers and ice sheets. So all of these sources are constantly exchanging with each other. Okay, yeah, there's a few fascinating numbers. Each year, 320,000 cubic kilometers of water evaporate from the oceans, and most of that falls back into the oceans. 60,000 cubic kilometers of water evaporates from the land, but 96,000 rains down. So the upshot is that there has to be a net 36,000 kilometers of water that must return to the ocean eventually to balance everything out. And most of that comes back to the ocean in the form of rivers. That figure is roughly the total flow of all rivers in the world. Some of that will sink into the earth, recharge groundwater reservoirs, and eventually come back. And there's a picture of it. Ooh-ah. Sir?
I have a question. With the, how far does the groundwater go down into it? I mean, there must be a level where you don't find any more groundwater.
Okay. The question is, how far does the groundwater go down? I'm not sure what the absolute limit is. I mean, if it goes down deep, since it gets hotter, the deeper down you go into the earth, eventually you would reach a point where the stuff is, turning to steam and then popping back out. And that is, of course, what happens when you have that. You have a geyser. I'm not sure what you're not in a volcanic zone like that, and it went down. Okay, if it sinks, I have no idea, but I've got a PhD, so I have to make an effort. If it sinks down deep enough, the deeper it gets, the more pressure it's under from the overlying rock. And if you take water or anything and you make it hotter and hotter and you increase the pressure, eventually you pass the critical point, which means that the water kind of forgets that there's a difference between a gas and a liquid. The difference between those two stages of matter just kind of goes away, and you have what's called supercritical fluid. I think they were getting some water, very, very hot water, in the super deep borehole on the Kola Peninsula. The Russians actually tried to drill an extremely deep well, and they got it to something like 40,000 meters before it got so hot that their drill equipment was breaking too often. And I think they did get some water out of that, but whether it was groundwater or whether it's the water that's actually dissolved in liquid magma, I'm not entirely sure. There are the physics of water in the really deep earth get kind of weird, and that's not really my field. For practical purposes, what keeps groundwater where it is that you have rock layers that are permeable to it and let it soak, and rock layers that won't let it soak through, that are impermeable to it. A permeable layer is called an aquifer, A layer that's not permeable is an aquitard. That's just what they call it. And in practice, groundwater sinking would probably hit an impermeable layer before it had gotten down as deep as it's physically possible for it to exist. So I think the answer probably is it depends on the arrangement of rock layers below the surface. The real answer is I have no idea, but you know, the PhD is a certificate of infallibility, so I have just created the very truth before your eyes. Okay, right. Okay, so there's the water part. The other thing everyone knows about the ocean is it gets salty. Water flowing over the Earth's surface always dissolves very small amounts of various minerals. Minerals that are present in soil, minerals that are present in rocks that it may be flowing over. Just by way of a quick example, rainwater is naturally just a tiny bit acidic. So when rainwater falls on an area of lots of limestone, like the Ozarks, for example, the rainwater will dissolve just a little bit of the calcium carbonate and probably a few other atoms in there of the limestone. And this, of course, is what gives you things like caves and sinkholes and the kind of topography that you find in the limestone plateau areas of the Ozark Mountains. Well, that dissolved stuff ultimately ends up in the oceans, and it builds up in the oceans because once it's in, it can't evaporate. Those dissolved salts coming from, let's say, the Ozarks get dissolved out by the streams. The streams run into the Buffalo River, the Buffalo runs into the White runs into the Arkansas into the Mississippi, and it all ends up in the Gulf of Mexico. When water evaporates from the Gulf of Mexico, the salts are left behind. There are other elements that can enter the ocean directly from the atmosphere, sulfur and chlorine. There's others that enter through hydrothermal activity. That is superheated water coming up from the bottom of the ocean, kind of like a super hot spring, except it might be 10,000 feet down. All of that is what puts the mineral content in the ocean. That's ultimately what makes it salty. Here's the thing. If this happens in a place like, let's say the Great Salt Lake in Utah, there are rivers and streams that drain into the Great Salt Lake. The Great Salt Lake being in a desert and not having any natural outflow, when water evaporates from the Great Salt Lake, the salts are left behind. And as you repeat that year after year, the salt concentration goes up until the Great Salt Lake is something on the order of 8 times as salty as seawater. Almost nothing can live in it. You might know that this happens in soil that's been heavily irrigated. When you pour irrigation water on the soil, and then the water evaporates, any salts that the water brings in is left behind, and you get increasing salinity in the soil until it starts doing damage to your crops. This is thought to be one of the reasons why the Mayans lost their empire. It goes on today in places like the Central Valley of California that are heavily irrigated. Why doesn't this happen in the oceans, though? Why doesn't the ocean collectively become as salty as the Great Salt Lake? The answer is that there are other chemical processes that remove dissolved substances. Calcium, for example, might erode out of limestones, pass down the rivers into the ocean. In the ocean, it gets picked up by living things, clams and snails and corals and things like that take it out of the water and convert it into their shells. There are chemical processes that will cause certain minerals to precipitate out on the bottom of the ocean. There are chemical reactions with the rocks of the ocean that might take others out. So you have some processes that remove salt and processes that add them. And when you have a chemical process going one way and a chemical process going the other, eventually end up at equilibrium. So this is why the ocean does not get constantly saltier. The processes that put salt in are in equilibrium with the processes that take salt out. These are some elements that are precipitating out. There are areas of the deep ocean floor that are covered with these lumpy black rocks. They're called manganese nodules. And they are rich in manganese, iron, copper. They grow extremely slowly, but this is one of the ways in which dissolved metals in ocean water are taken out by precipitation. These are, by the way, these have been looked at as sources of ore for metal. So far, last I looked, nobody had figured out a way to make it cost effective to take these things up from the ocean floor and refine them into metals. Ore on land is still more cost effective, more efficient. And this is a sample of deep sea clay. It looks reddish because it's absorbed some iron mixed in with the clay, the grains of which just look kind of irregular. You can see some rather regular things. Those regular kind of geometric shapes that you're looking at are pieces of the skeletons of living things, mostly a group called the diatoms. We'll talk about them later. They make skeletons out of silica. In fact, they are so good at it that if you grow diatoms in laboratory glassware, the walls of the glassware get thinner. The diatoms are able to pull silica out of the water so well that they can actually make it dissolve out of the walls of the glass that you're keeping them in. Kind of a neat trick there. Anyway, that's other ways in which dissolved stuff coming into the ocean is taken out. And then, of course, it's also done by things like mollusks. This very fine Amalacanthus zamboli from the Philippines is basically a bunch of calcium carbonate that has precipitated out under very carefully controlled conditions. Yes, ma'am? Oh, yeah? Mm-hmm. Okay, yeah. Okay, for those of you in computer land, she said she's from the Bahamas, and they've got shells like this as well. Yeah, snails, clams, conch, murex, dentalium tusk shells, for that matter, crabs will use some calcium carbonate in their shells. Corals are a really big one. Some single-celled creatures called foraminifera. There's lots of marine organisms that build skeletons out of calcium carbonate, and they'll take it just right out of the seawater. And then, of course, if this shell gets buried, it might stay in buried sediments for millions of years before finally getting dug up as a fossil or something like that. So this might actually, a shell like this might eventually become part of a new layer of limestone or something like that. Remember, we said that limestone eroding puts calcium in. Well, shells forming new layers of limestone will ultimately take it out. So things like calcium cycles on a very long time scale. Okay. Right, you still with me? Okay, these are the single-shelled critters called foraminifera. Each one of these is roughly the size of a sand grain. In fact, in several parts of the world, they are the sand grains. Though small, they're quite regular. Some of them look like little coiled snails, although they aren't snails. Some of them have other weird and wonderful shapes. These live in sediments. They float. Some species do in great number. And this is yet another type of living thing that can take dissolved minerals out of the seawater and convert them into a solid form. And there are whole layers of rock in this earth that are made of almost nothing but the shells of foraminifera, or forams for short. My major professor, when I was in grad school, was and still is a world expert on foraminifera. And he said they were great because you find them everywhere. There were fossils of them on every continent and living ones in every ocean. And in the course of his research career, he visited something like 150 countries. He'd done field work everywhere from Antarctica to Papua New Guinea. So if you're thinking about becoming a field biologist, find something that lives in a really cool part of the world, and then you can try to get grants to go study it. My other major professor worked on fossil snails, and the particular ones that he studied, the best places in the world to study them were the California coast and the French Riviera. Nice work if you can get it. Right, anyway. Never let it be said that I don't give useful career advice. Okay, this picture was taken by a famous submersible called the Alvin. I know people that have been on it. It basically is room for 2 people, and you can dive down to something like 8,000 feet. Military submarines don't go nearly that deep. If you tried to send a Los Angeles class attack sub down 8,000 feet, you'd crush it like a beer can against my grandmother's forehead. But the Alvin can get down really deep, and what you're looking at is a layer of muddy sediment made up of millions upon millions of shells of little foraminifera that have lived and died and sunk to the bottom and are forming these layers of chalky mud that will eventually harden into new layers of limestone. And then, given really long times, deposits like that may be recycled by getting thrust upward by forces in the Earth's crust that we call plate tectonics, which we'll be talking about in a couple of days. These are the white cliffs of Dover at the southern end of England. These days, everybody takes the train, but time was when you took a ferry across the English Channel from England to France. This would be the first thing you saw leaving France and crossing the Channel to England. You can see these white cliffs for miles, and they are made up of skeletons of microscopic living things made out of calcium carbonate. Like all of it right there. All of that is made up of this chalky rock made up of, I don't know, trillions upon trillions of living animal skeletons that lived and died in the oceans billions of years ago. And of course, now that they're uplifted and eroding, that calcium that makes them up is going back into the oceans. So I hope you get some sense of the total time scale that this is happening on, the cycling of atoms by the activity of living things coupled with erosion. This is supposed to be my whoa moment. I'm sure the folks online are going whoa as well. All right. So because these processes are in equilibrium that put dissolved atoms into the water and take it out, the ocean salinity is thought to have not made radical changes for at least the past 600 million years. It can fluctuate a little bit on shorter time scales than that, but it was fairly close to what it is now 600 million years ago. The average salinity is 35 grams of salt per liter, or 3.5% weight by volume. Okay, 35 grams of salt per liter. We also write this as 35 parts per thousand. You'll also see it written as 35 per mil. That's like a percent sign, except there's two little circles below the slash rather than one. You'll also see it written as 35 PSU, practical salinity units. If you want a chart, this is the makeup of typical salts. Almost all of it is 6 different ions. You can see chlorine is 55%, sodium's another 30%, sulfates and magnesium come next. And of course, there's lots of minor salts. Just about any element can be found in traces in ocean water, but good old sodium chloride makes up most of what's there. But it's not perfectly uniform. Yes, sir?
I'm not sure what an ion is. Can you just enlighten me a little bit on it?
Where what is?
Ion.
Ion? Oh, an atom that has an extra electron or is missing one, so it's got an electrical charge.
Okay.
Right. Like these two atoms walked out of a bar. And one of them said, hey, we've got to go back in there. I'm missing one of my electrons. The second one says, are you sure? And the atom says, yeah, I'm positive. Thank you very much. Yeah, it's an atom with an electrical charge because it's got an extra electron or is missing one. Okay, salinity isn't perfectly uniform. There are zones in the ocean that are a bit saltier than others. And there you've got a map. The purple areas are low salinity, as low as about 30 parts per thousand, with the red zones being considerably higher, up to almost 40 parts per thousand. So it's not perfectly mixed because it's so large. All right, a little bit as to why that's the case. You notice that most of the oceans are all connected into one, but you have some parts of the ocean that tend to be a little bit cut off from their surroundings. One example is the Mediterranean Sea between Africa and Europe, right there. You can see that that's considerably saltier than average. That gets up in places up to about 40 parts per thousand. And the reason is that A, it's nice and warm, so evaporation rates are pretty high. Because it's nice and warm, lots of beaches and sunshine and all that. There's not a huge number of rivers that flow in, so water leaves. And there's not a large amount of freshwater influx coming into the Mediterranean. I mean, except for the Nile over here. And then C, the Mediterranean doesn't mix very well with the Atlantic Ocean because it's connected only by a very narrow channel, the Straits of Gibraltar, if you've heard of those. So there is some water interchange between the Mediterranean and the Atlantic through the Straits of Gibraltar, but it's not that much. The Mediterranean does not mix as freely with the world ocean because it's mostly cut off. If you look up here, in between, this is Germany, and then above it is Scandinavia. There's this little purple blob right there. That's the Baltic Sea. And that's less salty than average. In fact, there's parts of it that are almost freshwater. The reason why that is first of all, it's also cut off from the main ocean. There's a narrow passage right here that connects it to the North Atlantic, but the circulation is not very free. There's not room for the waters to mingle very well. That little passage, by the way, where the Baltic meets the North Atlantic is called the Kattegat. And yes, that's the name of the kingdom that Ragnar Lothbrok ruled in Vikings. Yeah, that's where it got its name. It's less salty because A, it's colder up there, so there's not nearly as much rain. There's not nearly as much there's not as much evaporation, and there's more rain because it's colder and cloudier up there. So there's more rain, less evaporation, and more rivers. You can't see them on this map, but there's more rivers flowing into the Baltic, tending to make the water fresher than average. So you can have pockets of areas in the ocean that are a bit less saline or a bit more saline than average. Usually because they're kind of set apart from the rest of the ocean. They're only connected by a narrow strait, so you don't get free exchange of waters. Oh, what are some others? Some of these you can see are the mouths of rivers. I think that little purple blob on the coast of Africa, I believe that's the mouth of the Congo River. The mouth of the Amazon is right here. This tiny purple blob right there is the mouth of the Mississippi. That purple blob right there, that's the Rio Plata, I think. All of that would be, what's this, the Ganges and the Irrawaddy. So, yes, sir.
Where the Mississippi Delta is, I heard there's a dead zone there.
Okay. Okay, the question is, what about the dead zone at the mouth of the Mississippi? Can I get back to that later?
Absolutely.
Okay. All right. We'll have copious amounts of time. All right, I'll tell you what, it's 1:52. This would actually be a fairly good place to tie this off, and we'll pick this up again on Monday. Okay, any questions from the live people? Have I got you covered?
Sorry, I missed the first part. Was a little late.
Sorry?
I was a little late. I mean, I'm not sure what I missed.
Okay.
And I don't know what you mean by
Not very much. Okay. The questions are coming in. Will I post slides? The answer is yes. I'm going to go ahead and stop recording as soon as I can find the button that enables me to do it. Okay, we're stopping recording now.